Welcome. In this lecture, I want to give an example of a related rates question and how you would solve it. And then in the next lecture, I will summarize what we went through. So we're going to suppose that we have a company that has determined that demand for their product is given by this particular equation. Okay, where we're going to have that P is the price in dollars and Q is the quantity in millions. Okay, so the equation is Q equals the square root of 5,000 minus P squared. If the weather conditions are driving up the price $2 per week, find the rate of which demand is changing when the price is $40. So now there's a lot going on in this problem. So let's not get overwhelmed, and we're just going to go through it step by step. So the first thing that we want to do is we want to list the givens and desired values. So list the givens and desired values. And we have to be a little bit careful with this because there's different kinds of givens. Some of them are, particular values that you're looking at a rate at and things like this. We need to be a little bit careful. Okay. But in this step one, the first thing that we can do here is we want to let's kind of write down what everything is. So we have P of T, right, is going to equal the price in dollars. So we're looking at price, and we're looking at these in dollars. So that's good to keep track of. We know that Q of T is equal to the quantity, okay, in millions. And then we have, so along with these then, so then we know that dP dt, right, is going to be the change in price. So the rate the price increases at. So this is the rate the price is going to increase at. And dQ dt is going to equal the rate that the quantity increases at. So this is going to equal the rate that the quantity increases at. Okay, and so that's just kind of, these just came from, it's just the definition of what it means to take the derivative with respect to t. That's, okay, but these were given as the variables for those quantities. Okay, so now what else are we given? So we're given that well, we know that, so somewhere in here we have, if we look at this, we have that, so if the weather conditions, so the weather conditions are driving up the price, okay, so they're driving up the price, so this is a price increase, $2 per week, okay, so we have that, we're given that, so from that right there, we're going to have that dP dt equals, so we have $2 per week. But we're going to notice something kind of in there, which is that, we're looking at the rate that the demand is changing. Okay, so let's actually underline that because we're going to come back to that. So we're going to want the rate at which the demand is changing. Okay, and so the last thing that we have kind of in here is that when the price is $40. So we're looking at all these values only knowing, like, this is when P equals $40. So there's actually there's another way to write this then, which is that to write dP dt evaluated, so this is when P equals 40 is going to equal 2. Okay, so that's kind of another way to write that. And so then we want, well, we want to know dQ dt, right? So this is, we want to find, so this is, we're looking for dQ dt. So these are two different colors. I hope that's clear. Okay, so we're going to find dQ dt, and this is again when P equals 40. Okay, because that's still coming from that same place. Okay, so we can actually still, right? So again, this can be written as we're looking for dq dt when p equals 40. So we want to know what that's going to be. Okay, there's a cautionary tale here, which is don't sub in p equals 40 till we're done differentiating. Okay, so this is our caution. So don't sub in p equals 40 until we're done differentiating. This is like the most common mistake, things you learn from having taught classes a lot. Okay, and we'll keep that warning at the bottom because it's going to be important. Okay, so that was step 1, so now we're going to do step 2. Okay, so the next thing that we want to do is we want to relate these quantities, right? Because we're going to be looking for dq dt. And to get something with dq dt using what we know, which is a dp dt and a p-value, okay, how are all those things going to show up? We're going to relate q and p, then we're going to differentiate with respect to t. And when we do that, we have a relationship between p and dq dt and dp dt. Okay, so let's go ahead and do that. So we have that, so relate P and Q. Okay, so in this circumstance, we can use it. This just comes from right here. So here's our relating equation. And in some, this one's given to us. You might actually have to figure it out. So Q is going to equal the square root of 5,000 minus P squared. Okay, so that's our relating equation. And then we have, in the next step, right, we need to bring in our dp dt's and dq dt's. So what we need to do in the next step is we actually need to use the chain rule to differentiate both sides with respect to t. Or you could say this to kind of abbreviate. So we're going to take, right, so if you want to say, we're going to take d dt of both sides, which is just differentiating with respect to t, but we need to use a chain rule because these are both functions of t. Okay, so let's go ahead and do that. So I have d dt of, so here's the left-hand side of that, so this is q, is going to equal d dt of, and then I take the right-hand side of this here, so I have the square root of 5,000 minus p squared. Okay, and so on this side, I'm just going to get, so I have dq dt is going to equal, and then we're going to do this a little bit carefully because it's some tricky stuff in here. So we're going to take, we're first going to take the derivative, like treating p as a constant, and then we're going to have to multiply. So we're going to have, oh, the other thing I want to point out here is that this here, remember, is 5,000 minus p squared to the 1/2. Okay, so we're going to get, now I think I'm ready to write this all down. So we have we have 1/2 5,000 minus p squared to the minus 1/2, right? This is just treating this like a power. We're using the chain rule, but now we need to take the derivative of this using the chain rule. So now we get minus 2p. Right? So I just took the derivative with respect to t of this, so I get minus 2p, but now I still need to take the derivative with respect to t of this, so I get dp dt. Okay? So what's going on here is that I can sub back in. So now that I've done all my differentiation, I have this relationship between dq dt, p, and dp dt. So I can kind of sub this in everywhere. So I have that so step 4. Okay, so I want to sub in my p-value of $40. So sub P equals 40. So I'm going to see P here and here. And what's the other thing that we have is that dp dt equals 2. And dp dt equals 2 into this thing we have here. So kind of simplifying it a little bit. So we have dq dt equals, because I have a minus 2 and a 1/2, so I end up with minus p, and then I have 5,000 minus p squared to the 1/2 dp, oops, let me switch those, so it should be dp dt. Okay, so this has got to go here, so we've got here, and here, and here. Okay, and so what we end up getting, and this is this dq dt that we're interested in, so we're going to get that dq dt is going to equal, so then I can just kind of put these in, so I have minus, and then I'm going to put on my parentheses, you know, the trick I like to do to put parentheses first, and then you can fill it in later so that you don't get yourself confused. So we have 5,000 minus, and then I've got a p here that I've got a squared to the that should be a minus 1/2 to the minus 1/2, and then I have my dp dt, and I know my dp dt is 2, my p is 40. Okay, and so what I end up getting is approximately 1.37. Okay, there is a final step, but we don't have to do this because in this circumstance, dq dt is already solved for. Sometimes you'd actually have to isolate it, but dq dt is already solved for. Right. Oh, this is minus 1.37. Okay, and the minus there says it's falling, so the demand is, and again, because it's a minus, and this is a rate of change, this is a falling by 1.37 million items per week. Okay, and that's like my final answer. So what is going on here? We have that we have a mess of a thing up here, but it relates some quantities and some rates and so on. Okay, so we kind of sort that out in the beginning. We know that P of t is price, Q of t is quantity, which then tells us that the rate the price increases at is dp dt, the rate the quantity increases at is dq dt, and we kind of look then through our statement to try to figure out what we have. And we need to be really careful about the fact that all of this happens when P equals $40, but you don't plug that in until the very end. Because P is a function of T, so when you're differentiating, it's like in any of these circumstances, when you're differentiating, you don't put in the specific input value until the very end, okay? So we have that, we have that dp dt is going to equal $2. That came from driving up the price $2 per week. And this is all happening when P equals 40, is told here. The rate at which the demand is changing is what we're actually looking for. How do we relate dp dt, dq dt, and P? We do that by taking this equation and then differentiating with respect to T, remembering that P is actually, and Q are actually functions of T. So we end up having to use the chain rule twice here. And we do that, and then once we've done that and gotten this equation, then we can start plugging in our actual values. So we waited until this point to plug in the P equals 40. That's really important. That's a very common mistake. And then at that point, we can solve for dq dt. At this point, it's already isolated because of the particular function. It might not always be. And because we got a negative value for DQDT, that told us that we were actually looking at the rate at which the demand is falling. Okay, so I hope that made some sense, and I will see you in the next lecture.